Let's try to solve this problem here. You have two thin lenses with a focal length of magnitude 12.0 cm. The first diverging and the second converging. So that's plenty of information. Let's try to write it down. We know that we have two lenses over here. So the first one is diverging. So first diverging. Because it's diverging, we know that the focal length should be negative. So the first lens, we are going to write as f1 is equals to negative kind of focal length, so negative 0.120 meter. So that's for the first diverging lens. The second one is converging. So because it's converging, we know that the second lens, the focal length should be a positive focal length. So f2 will be positive 0.120 meter. Okay, at the same time, we know that because it's diverging, the characteristics of the image can only have one type of characteristics, which is virtual, upright, and diminish. Okay, virtual, upright, and diminish. So because it's virtual, upright, and diminish, we should expect that when we determine the image from the first lens, V1, the image distance should be negative because it's virtual. Then the magnification for lens number 1 and the image of lens number 1 should be positive because it's upright. Then the modulus of magnification 1 should be less than 1 because it's diminished, and your V1 should be less than U1, and our HO1 should be less than our HI1, sorry, height of image. Image 1 should be less than height of object 1. So this is what we know based on the lens. It's diverging, then it's virtual, upright, diminished, then we know these are the properties of it. If it's converging, the characteristics can change based on the position of the object, so we cannot be very clear, we cannot know for sure what kind of image will be formed. What can we know is that a converging lens with a positive focal length. That's what we know for now. Okay, so they say that these two lenses are located 9 cm apart. In terms of mathematics, you can't really write it as u is equals to what or v is equals to what. There's nothing you can write. But I think for this kind of situation, right, when it involves distance between lenses, right, it's probably a good practice that you draw the situation. Okay, you sketch a simple sketch will do. So you have your optic axis together with your two lenses. The first one will be a diverging lens. The second one will be a converging lens. They are located 9 cm apart, so you draw their midplane and you say that they are 0.0900 meter apart. Okay, we'll definitely use this value later, but for now we cannot express it in terms of u or v or what, okay, because we don't know the position of all the object, image, and everything. Okay, so we just sketch this diagram here for now. An object 2.50 millimeter tall. Okay, so now they say this is an object, and the object is, let's write as O. O is 2.50 mm tall. So if you write in terms of mathematical symbol, this is the height of the object because it is to the left of the first diverging lens. So this is the object for the first lens. So you can call this as HO1. HO1 because it's object is start with upright. Okay, you won't invert the object in the first place. So this one will be positive 2.50 times 10 to the power of negative 3 meter. So this is the height of the object initially. Then they say that it's placed 20 cm to the left. Okay, so place 20 cm to the left. Okay, it's a bit messy, but I hope you get the idea. 20 cm to the left, that is the position where we place our object, right? Position where we place the object. So this one is the object distance. So because it's with respect to the first lens and it is the object for the first lens, so we're going to call it as U1. U1 is positive 0.200 meter. Why positive? Because if you look at the first lens over here, the incident will be on this side, the refracted will be on this side for the first lens. Then afterwards, if you move on to talk about the second lens, then this will be the incident side of the second lens. This will be the refracted side of the second lens. Okay, so for now we are still talking about the first lens, so let's don't rush towards the second lens for now. Focus on the first lens, diverging lens. Okay, so we extract all the information that we can from the problem statement. So let's continue to look at the question. How far from this first lens is the final image formed? Okay, so they want to know with respect to the first lens, where is the final image? So we can probably do it step by step. Find the image for the first lens first, then use the image for the first lens as the object for the second lens. Then once we use the object, we determine the position of the object for the second lens, and we find image for the second lens. Okay, we do it step by step. So focus on the position first, maybe. Okay. So I'm going to write A. What we're going to do, we are going to do the standard lens equation. 1 over u1 plus 1 over v1 is equals to 1 over f1. We are focusing on the first lens over here. I think we have all the value we need. We have u1 is equals to positive 0.200. v1 is what we want to determine. And f1, we have f1 is negative 0.120. Okay, so if you calculate this, I believe you see that v1 is equals to negative 0.075. Okay, and since it's negative, it means by your image here is a virtual image, and because it's a virtual image, you should expect that your image is on the opposite side of the refracted ray. Okay, so refracted ray is on the right hand side of the lens. Your light will shine onto the lens from the left hand side, then you get refracted and come out from the right hand side. So because the image need to be on the opposite side of the refracted ray is on the right hand side, so the image is on the left hand side. So that means that if you want to label where's your image should be on the left hand side. Okay, so let's put in everything that we know regarding the information here into this diagram. So this is a diverging lens. So a lens has two focal points on each side of the lens. So this is f1 and f1 representing the focal point for this diverging lens. And we know that the distance for focal length is 0.120 on extending from both sides of the midplane. Okay, so this is for diverging lens, and is for this information over here. The second lens also have its own focal point as well, so I'm going to label it using the blue dot over here. So these are the focal point for the second lens, the converging lens. And if we determine the length extending out from the second midplane, well, the distance is again 0.120 meter, 0.120 meter. Okay, so these are the focal point and focal length. Then we know that the object is being placed somewhere over here. It's supposed to be 2.50 millimeter tall, which is something very short, but for illustration purposes, I extend it to be slightly taller so that we can see the position of everything more clearer. Okay, but for now, what we want to emphasize is that the object is placed 20 cm from the first diverging lens. So if you measure the distance from the first diverging lens midplane, is 0.200 meter. Okay, now that we already determined v1 is negative 0.075, again opposite of refracted ray, which means by from the diverging lens, we are going to look at it to the left. Okay, the image will be on the left of the diverging lens, so extending from the midplane to the left. Okay, so this is 0.075 meter to the left of the midplane of the first diverging lens over here. Why is it left? Because it's negative. The image is on the opposite side of the refracted ray. So this is our image over here. So now this image here will be the object for the second lens, the converging lens. So because it is the object for the second converging lens, we need to determine the distance, the new object distance, or u2. That's what we want to determine right now. So u2 will be the distance between the object, which is this arrow over here, from the second converging lens midplane. So this is the distance that we are interested in. Okay, we will be using the 9 cm apart information right now, because it's 9 cm information over here. We'll combine it with the distance of the image from the first diverging lens. This distance and this distance here allow us to know the object distance for the second lens. Okay, this second lens over here, the object distance 0.165 meter can be obtained by taking the image distance from the first lens, this is 0.075 meter, add it up with the distance between the two lenses, which is 0.0900 meter. that allows us to obtain the object distance for the second lens. Okay, if you want to put it mathematically, what you can do is you can say that u2, okay, u2, let's put modulus, we don't want the sign to confuse us. Basically u2 will be taking v1, which is 0.075. okay, you are going to take this value, add up with the distance between two lengths, right? So you're going to put 0.0900 over here. Okay, so substitute v1 is equals to 0.075 plus 0.0900. So this is what you get 0.165 meter. Okay, so that's u2, and of course you know that u here is positive because your object is on the left hand side, your incident ray is also on the left hand side of the second lens. Okay, object is on the left hand side, incident ray is also on the left hand side, so they are on the same side, so u here will be positive, so u2 will be equals to positive 0.165 meter. Okay, so now you have obtained u2. You can use u2 over here to find v2 right now. Okay, so 1 over u2 plus 1 over v2 is equals to 1 over f2. So 1 over u2 over here will be positive 0.200 plus 1 over v2. We want to determine v2. Why 0.200? What am I doing? u2 over here, we actually calculated earlier. This is u2, you can just put it in, positive 0.165. Then f2 over here, we can determine f2 from up here, so this is positive 0.120. Okay, so put everything in, you can find v2, and you determine v2 to be equals to positive 0.44. Okay, so if you want to label it, this is the image that is formed, and if you want to determine the distance, it's positive. So positive means by it is at the same side as the refracted ray. Your image, it will be same side as the refracted ray. So since your refracted ray is on the right, so it will be measuring from the second lens midplane to the right for 0.44 meter. So this distance here is 0.44, extending from the midplane of the second lens to the right because it's positive. Okay, so positive means I same as refracted ray. Refracted ray is on the right hand side, so image is on the right hand side. Okay, so here this diagram will illustrate clearly where are the position of the object, the image, and the second image all in their correct position with their correct length measurement. So I hope this diagram will help you to understand everything clearly. In an exam, I think it's good to have a rough sketch of the position of everything, because I believe if you don't sketch it, it will be quite difficult for you to get this 0.165 meter over here, because you need to see that it's actually an addition of the image distance for the first lens I1, the V1. You have to add it up with the distance between the two lenses in order to get the object distance. Sometimes it's a pause, sometimes you need to add, sometimes you need to subtract. It depends on where your image lands on. Sometimes your image can land to the left of the lens. Sometimes it can land to the right of the lens. In this case, it's a diverging lens, that's why it's always on the left. But let's say if you start with a converging lens, then your image might be on the right, might be on the left. So for those situations, it is more complicated. Then I really highly suggest you to sketch the position of everything in order to determine the object distance for the second lens. That's actually quite important. Okay, so how far from this first lens is the first image formed? So they're not interested with V2 actually. They want the position of the image from the first lens. So that means they want this distance from the midplane over here to the image over here. So you can see that it is actually an addition of 0.440 over here, adding it up with the distance between the two lenses. Then we are able to get the distance of the image from the first lens. Okay, so let's write it down. I don't have much space, so let me write it here maybe. Okay, distance between what again, I2 and first lens. Okay, Okay, so that will be taking 0.440, add up with the distance between the two lengths, which is 0.090. So if you add it up, I believe you'll get the distance to be equal to 0.530 meter. Okay, so that will answer question A. So the distance from I2 to the first diverging lens is 0.530 meter. Okay, so that answer questions A. Questions B, is the final image real or virtual? Well, it's positive, so it's real. Okay, so question B, image is real. Image is real because V is positive. Okay, next, what is the height of the final image? Is it upright or inverted? Right now I'm representing it as upright, but actually I don't really, it's just a guess. If you look at the calculation here, you cannot determine it for sure. Because for two lens situation, real doesn't always mean inverted, and if it's virtual doesn't always mean it's upright. Okay, for two lens situation, you cannot just pair up virtual to be upright, real to be inverted. You have to look at it from a case by case basis. Okay, so we are going to analyze it slowly. We are going to calculate HI1 first, the first image height. Then we are going to use the first image height as the second object height. So HI1 will be equal to HO2 first. Then from there you find the height of the second image. So if the height of the second image is a positive value, that means it's upright. If the height of the second image is a negative value, that means it's inverted. So that's the strategy we are going to be taking. And I'm out of state over here, so I'll continue my question C over here. So I'll start with the first lens over here first. So for the first lens, first diverging lens, I know that negative V1 over U1 will be equals to HI1 divided by HO1. Okay, I have the value of both V and U, so I'm going to substitute. V1 is equal to negative 0.075. U1 is equals to positive 0.200. So that's V and U. HO1, the height object 1 is positive 2.50 times 10 to the power negative 3. That's HO1. So we can determine HI1 right now. Okay, so if we use our calculator, we can find HI1 to be equals to positive 0.9375 times 10 to the power of negative 3. Okay, so around 0.94 millimeter, somewhere around there. So we can see that the height of image 1 is a positive value. That means by this time it's a virtual and upright image. Virtual because it's negative for V1 over here. Upright is because HI1 here is positive. Okay, but they're not interested with this image, they're interested with the final image. So we have to continue and say that HO2, height of object 2, will be the height of object 1. So therefore, we can say that HO2 is equals to positive 0.9375 times 10 to the power negative 3 meter. Then afterwards, we can continue to the second converging lens. For the second converging lens, we are going to do the same thing actually. So negative V2 over U2 will be equals to HI2 divided by HO2. So negative U2 over here, we have U2, the value of U2 is positive 0.165, positive 0.165. V2 is over here, positive 0.44, positive 0.44. So it's equals to HO2, we have HO2 up here. So this is positive 0.9375 times 10 to the power negative 3. So what you can get is HI2. So HI2. So if you calculate, you get HI2 to be equals to negative 2.50 times 10 to the power of negative 3. Okay, so from this calculation over here, we see that HI2 is actually a negative value. So this negative value means by the final image is inverted actually. So final image is inverted. Okay, and since it's inverted, my diagram is actually incorrect. I'm not supposed to label I2 over here. I'm supposed to label I2 to be pointing downwards and label I2 like this. Okay, so I highly suggest for this kind of characteristics, if it involves two lenses, right, especially two lenses kind of question, don't simply assume that real is inverted, virtual is upright. In this case, it is true because V2 is real, so your image is real and it's inverted. Okay, that follows the pairing that we mentioned usually. But for two lens situation, you can sometimes encounter virtual and inverted cases. You can sometimes encounter real and upright cases. Okay, so I think it's always good to do this kind of calculation. Going from the first lens, find the height of the first image first, then take the height of the first image to be equal to the height of the second object, and from there determine the height of the second image. And from there, if it's positive, then you know that it's upright image for the final image. If it's negative, then the final image is inverted. Okay, do it step by step, and I believe all answers can be obtained. And again, sketch a diagram over here to keep track of the position of everything, so that we can determine the relationship between all the lengths carefully. Okay, so that's it for this question. Thank you very much.